Welcome to topic 8.4, electric fields of charge distributions, daily video number 3. In this video, we will explore the resultant electric field at the center of a semicircular arc while changing the amount of arc that is missing. My name is Easton Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. So just like we had before, we had this amazing process that we're going to follow and once again use throughout this video. So let's look at our example. In particular, a ring, a solid ring of charge. So unlike last time where it was offset along the axis, we're directly in the center of this ring of charge. I want to know the electric field in the center of the ring. Okay, well, let's hop to that process.
Wait!
Whoa, who are you?
I'm you, from the future.
Really? You look terrible.
Rude? No. We don't have time. Don't try and solve the problem.
Why not?
We don't have time.
Okay, why didn't you just come back earlier?
No, that's not what I mean. On the AP exam, time is a precious thing. You can't just jump straight into solving. You should always think about the problem first.
Oh, is that it?
Yes. Don't make the same mistake that I did, or that you did. This is all so confusing.
Okay, well, thank you.
Remember to think.
Okay, well, that was fun. Hopefully I'm okay wherever I am. But let's stop to think about this. He said to think. So can you make a claim? What do you think the answer is? Yeah, it's just going to be 0 due to symmetry. Oh my gosh, thanks, future me. We save so much time by not doing all that work. Why is this in here? Always pause and think about symmetry to see if it's simpler than you might think before you go jumping into a problem. I don't think we're going to see me again, but you will as you keep watching this video. So let's look at this partial ring of charge then. For a partial ring of charge, if I have a little bit missing, I don't quite have that same thing canceling out. I have this component here that has this section on this side that's still going to be able to push my electric field that direction. So because that's the case, this is not going to cancel and be 0. So we do have to actually solve this problem. Looking at our electric field that we have there, we're going to know it's going to be just the x components because all the y components are going to cancel themselves out. So that's ultimately what I'm looking for when I solve this problem. So setting this up, I have my tiny little dq element, my differential charge, and I have a tiny little thickness ds, which is my arc length. And there's my r, and once again, my r hat. My density of this ring is going to be dq over ds. Where I have to keep in mind for this charge density lambda, it's just going to be for that ratio. If I were to give you the full charge over ds, it'd be a little bit trickier because I have to solve for the actual arc length with just some fraction of a circle. So by keeping it lambda, pretty nice and happy. Okay, but back to this. I have this ds and this dq, but there's another way I could write this. I can write this in terms of d theta, where there's this tiny little theta element that's resulting in a ds. What is that equation? Well, ds, tiny little arc length, is equal to r d theta. So making that substitution for lambda, I can manipulate that around, and this is what I want to save for later to sub in for my differential charge in terms of theta, because that's how I plan to integrate it. Could you have kept it in terms of ds? Sure, but you're going to see why putting it in d theta makes it a little bit happier for our particular case. So looking at symmetry once again for our ring of charge that we have here, we have our dE going down, we have our x component and our y component, and just like last time, that y component is going to cancel out for all of our elements because we have the same amount on the top side that in the bottom, it's the right and left that isn't quite going to cancel. So once again, looking at our theta and our adjacent side, which is our x component, we do cosine, making our substitution. And as we plug that in, we're going to get an equation that looks like this. We're trying to find our electric field that's just the sum of all those little dex elements, which can be written in terms of cosine theta. From earlier, we know what our dq is. So if we plug that in, ta-da, we're going to get this for the magnitude of our differential electric field element in terms of our d theta. Well, I don't just want a little bit of electric field. I want all the electric field. So sure enough, we do have to take the integral of that. So making that substitution, we're going to get an equation that looks like this. Doesn't seem too bad as we move right along, subbing in our r, because this r at every single point is just the radius of our arc. It doesn't change length because at every single point along the way, it's just r. So we make that substitution, and that's going to allow us to sub that in, simplify it to pull out all of our constants. And once again, we're left with this equation. That actually seems pretty happy because with all these constants, cosine theta, d theta, we can totally integrate cosine with regards to theta. But before we do, let's talk about bounds. So now that we've made that wonderful equation, right, we need to start plugging our bounds in to actually solve this for when 60 degrees is missing. So once again, we're looking at this thing from cosine theta, d theta times that I hat, and we're looking at our part that's missing here. We're trying to find how much of this electric field we're trying to integrate into that one particular direction to the right. Well, the space that's missing, I can do it in terms of the mathematical way of doing it. We're going kind of from up here, which is 30 degrees, to negative 30 degrees, which is below that line. When we set this up that way, we're going to see that we're kind of seeing all these little negative 30s to 30s that are going to look something like that. So we have that one, that one, that one, that one. There's technically an infinite number of these electric fields, the tiny little infinitesimal electric field elements that are pointing different degrees to the right. As we integrate that, that's one way we can set this up. Another way we could set up our bounds, which is actually kind of my favorite way of doing it, we can actually cut this thing in half. We can do just the top part. So we're integrating from 0 to 30 degrees, 0 to 30 up here at the top. But because we're only doing half of it, we have to double it. Why are we allowed to do this? Because it's symmetric across that x-axis. So I know that whatever the electric field would be in this direction, in the x direction, it's going to be the exact same amount on the bottom. So we're just doubling that amount for the top and the bottom. And you're going to see me work through the rest of this example and the other examples using this kind of idea. But either one is absolutely valid. Okay, let's kind of actually apply this to solve for our answers. Here's our equation from the previous page. E is equal to 2, 1 over 4 pi epsilon naught, lambda over r, and the integral from 0 to 30 of cosine theta d theta I hat, where I hat once again is our vector. If we take the integral of cosine, we're going to get sine. And if we plug in our bounds of integration, we're going to get sine of 30 minus sine of 0. If you happen to have your unit circle all memorized there, yes, sine of 30 is just 1/2. And then our sine of 0 is just going to be 0. So applying this whole thing through, we get the equation that our E field is equal to 1 over 4 pi epsilon naught lambda over r times I hat. That is the resulting value when we have that 60 degrees missing from our arc. But here's a question for us. How much of the circular arc should be missing to have the greatest possible magnitude of the electric field at that center? So take a moment and think what angle should be missing to have the strongest electric field. So make a claim. Well, perhaps you're thinking the answer is going to be 180 degrees missing, and you would be absolutely right. 180 degrees missing gives us the maximum amount of electric field pointing to the right. Why is this the case? Because when we look at our 0 to 90 degrees for our integral, there's nothing pushing back the opposite direction. All of these electric field lines, as we can see here, referenced in orange, have either a vertical component or a rightward component. There's no component of the electric field that's pushing to the left. So this maximizes that electric field. Even though it's canceling out the vertical amount, it has the most going to the right. So setting up our integral, we have the same integral as before, 2 times 1 over 4 pi epsilon naught lambda over r sine of theta, but now we're going from 0 to 90 degrees when we do our integral instead of 0 to 30 like we did last time. And if we do that integral, we're going to get 1 over 2 pi epsilon naught lambda over r I hat. Well, as a comparison, 60 degrees missing was this much. 180 degrees missing was this much. So sure enough, 180 is greater than 60. In fact, it's 2 times greater for that kind of angle that is missing from our arc. Let's give one more try here. If I have 300 degrees missing for a charged arc, how much does the magnitude of the electric field at the center compare to when there's only 60 degrees missing? Or more simply put, will there be more or less resulting electric field when there's 300 degrees missing? Give this a ponder. Okay, well, here is our answer. If I'm going from 0 to 150 and I do my integral and set this thing up for my bounds from 0 to 150, I get 1 over 4 pi epsilon naught lambda over r times I. Wait a second. Those are the exact same. Tricked you. Maybe not. Maybe you got this one right. But yes, they're the exact same electric field. Okay, now the math says so. Let's talk about this conceptually to see why this is the case. So if we look at 60 degrees missing, it's going to look something like this. If we have 60 degrees remaining or 300 degrees missing, it's going to look like that. So sure enough, these two are the exact same outcome, but why? Conceptually, it's because this top portion and that bottom portion that are in orange perfectly cancel themselves out. The result of just this top orange section would be a net electric field pointing down. The result of this bottom portion would be a net electric field pointing up. Because it's the same amount of arc and the same distance away, those cancel, leaving just this purple region. Well, this purple region is the exact same amount of space as this purple region. So that's why in the end, they end up being the exact same. This is an example where we don't necessarily have to plug the numbers in. And again, you're welcome to do so to actually calculate it. But if we conceptually reason through the problem, sometimes that can simplify and speed up our process as we go through, thinking about the symmetry of the problem and what's actually causing the net electric field at that center point. So what should we take away for this video? Probably the biggest things to take away is that you should always conceptualize the problem before you solve, right? Don't have people coming back from the future to tell you you done messed up somehow. Symmetry is always there to help. So as we saw in that last example, we had the top portion, the bottom portion canceled, leaving just the x component that was going directly there to the right. And whenever you're solving these problems, when you begin, but even all the way through the end, always follow a set procedure each time you solve to help reinforce the similarities. If you're doing it a little bit differently every single time, you might miss some of the patterns, some of the symmetries that help make these problems a little bit simpler. So with that, thank you so much for swinging by for this video, and I look forward to seeing you at the next one. Bye.